Well, I mean, it's an incredible amount of work and really has great potential. I mean, most all of my comments, and I kind of, sort of based on what you said when we first sat down and talked, if you want to turn this into a journal article, I kind of approached it from a standpoint of a reviewer of an article. So I have
Thank you.
many editorial comments in
Good.
here, particularly as a way of kind of tightening things up. I think one of the previous questions helped a lot because you throw out the term Darcian, and I'm like, okay, I know Darcy's Law, but
So what does that mean?
yeah, how
Yeah.
was this done? And particularly in looking at something like this, I mean, this was very helpful, but it's going to be important to put error bars on both of these.
Sure.
And so you can kind of put it within that type of context. Also, the Roslev.
Oh, yeah, there should be an H. Horselev.
Horselev?
Yeah.
Okay, that also, I think, what is the Horselev?
So I assume that you're referring to the equation 2K to the Horselev K?
Well,
for the Shelby Tube?
Right,
Yeah.
the Shelby Tube.
So what we did is we can use that same data of head as a function of time and evaluate it using the following head equations.
Okay.
So that comes from Horselev 1951. So that's where that name comes from.
Yeah, I could have gone and looked it up, I suppose, but on the other hand, a sentence or two of explanation what that might be.
Oh, okay.
Or what, as well as the Darcian approach. Maybe you could sort of put the screen up real quick.
Sure.
Real quick.
Draw some pictures.
I just have one simple question, if you've got a marker. Write the symbol for sulfur, what is it, sulfur?
Oh yeah, Kip pointed that out. I do have that wrong. I have it in the text as this, where it should be this.
Okay, good.
Yeah.
Glad you recognize that.
Yeah, that was.
It's not just that compound, it's all of them.
Oh, right.
Yeah, okay. That's basically the gist of my questions and comments.
Okay.
Vic?
Yeah, I agree with Paul's really well done, not just piece of research, but multiple pieces of research. And I thought it was a really good job, very involved for a master's level study. Most of my particular comments you got through my review copies that I sent you earlier. So these are just some questions I have based on the presentation today.
Sure.
And I have a few, so I've tried to prioritize them, but I don't need to go through them all. I'm curious, you mentioned that the Shelby Tube is an accurate at low gradients of about 0.01.
Correct.
And that's meters per meter, or unit length per meter.
Yeah.
And typical regional groundwater gradients are usually less than that. So I was wondering if you could give us some context of what the gradients are in West Bear Creek. I assume the vertical gradient is much steeper, but do you have some range to kind of help couch that 0.01 to put in perspective?
Yeah. The gradients. I would get that information from the Darcian, from the piezo-manometers. And it does vary from as low, well, they had an amplification factor of roughly 12, and they were willing to measure to about 0.5 millimeter. So that, what does that turn into? 0.05 divided by 12, so an order of magnitude divided by 36. So, I mean, a 10,000, something on that order is what they were willing to measure. How reliably that is being measured?
That's the low end of the gradient.
That's the low end,
What would be the high end?
And up to a centimeter.
Okay, so
Strong gradients.
So were you having a lot of flow, the gradient is much above 0.01?
Yes.
Okay.
Yes.
Well, also, it's the flow and the permeability.
Right.
Right, so it's the interplay of the two.
So if you have areas of very low permeability
Yeah.
and very low gradient, that's going to be particularly difficult because that would cause low flow, which is really what we're getting at. It's just hard to get the low flow.
Yeah,
Okay.
yeah.
Do you want to alternate? Do you have some questions? Do you want me to go through a couple more?
You can, no,
Okay.
carry on.
All right, thanks. I found it interesting that both tanks at the U and Denver show that the upward Shelby Tube Q is less than the downward. And I'm wondering if that could be something to do with the way the Shelby tubes were installed. You know, you pound them down in. Is there something that's causing some anisotropy as you put it in? And I don't have the answer to this. I'm just wondering if you could conjecture a little bit. Is there some way to test that by maybe pounding them up in some situation?
Right.
Then it switches. And I don't understand this myself, what could happen in terms of compaction and the shear on the materials going in, but I found that interesting that you found it in both places.
Yeah, and that is a very interesting finding, and I don't have a great explanation for that. You know, what you're suggesting is kind of that the vertical hydraulic gradient or the hydraulic conductivity is being changed, but I don't see why that would depend on the direction of the flow.
Or the direction the tube's pounded in.
Or the direction.
So when they're both in the same direction, you get more higher Q than when they're in opposite directions. You pound in opposite the flow direction.
Right. So that could be, you know, I don't know, like that if this is the wall of the Shelby tube and you're getting some sediment grains that are doing this kind of thing as you're pounding it down in, so that you're creating a slightly different conductivity upwards and downwards. I don't know.
It doesn't make sense to me either.
Yeah.
I just, food for thought.
Yeah, sure. I've been really racking my brain why that is different, and I don't have a good explanation. It's just a very interesting finding.
Yeah.
But it's very consistent, you know, here in Denver, it's,
Interesting.
yeah.
Just a couple more. And this is more a chemistry question, it's sort of side light, but
Sure.
the plot showing the dissolved gases
Sure.
versus the noble gases showed a very high CO2 and methane.
Yeah.
And in fact, O2 and N2, which is just very different than atmospheric concentrations.
Yeah.
Could you just explain a little bit why, particularly CO2 is so high? In both, it's not obviously because of the blankets, it's just real, it's a real signal.
Right.
What is causing that high CO2? Is there some plant respiration decay that's going on that explains that locally, or is that more a regional flow phenomenon from the nitrate loading in the agricultures to the discharge?
That was going to be my suggestion. I'm not sure if it's a regional or local event, but in North Carolina, there's a lot of detrital organic material, so there's a lot of microbial activity in the subsurface. So whether that's really from the aquifer or it's from the riparian zone isn't overly clear, but I can say that it is probably from the aquifer because the concentrations across the transects do not vary a lot with respect to CO2. So, you know, if it was more of a riparian kind of derived CO2, I would expect the edges to have more than the center, but it seems to be pretty consistent across the transect.
And perhaps that might be related to my next comment, is that the oxygen's really not that low. And
Yeah.
typically where you see high methane or high CO2, you see low oxygen. But you've got both. And I was wondering if you also looked at excess air calculations based on the noble gases. Is this really high excess air in these samples?
That is being looked at. There's a few that have some excess air. A lot of them are pretty modestly stripped.
Huh.
So that is something that Kip and Troy have been trying to kind of figure out is what's an appropriate excess air model to use for these noble gases. But as far as I know, we're still trying to figure that out. So
90% of the samples are stripped,
Okay.
not massively,
Right.
but that makes, so they could have had a bunch of excess air to begin with, but then they got stripped, and so you can't really tell how much they had.
It's just interesting that the carbon dioxide particularly is so high. And I know that wasn't the
Yeah.
main part of your thesis, so I don't want to dwell on it, but it was interesting.
Yeah, I mean, the whole high-freak zone and subsurface reaction is really kind of where the research led me to. It is not really what we intended for these devices.
Sure.
So, yeah.
But John, just from your chemical background,
Mhm.
from an equilibrium point of view, if things were in thermodynamic equilibrium, should you have oxygen, CO2, and methane all in the same samples?
No, I wouldn't think so.
Well, that's times 100, right? So the
Right.
methane is
It's a
invisible.
very
Oh,
small.
I didn't see that. Oh,
Yeah,
okay.
yeah.
Oh,
So O2
my-
is times 100
Oh,
as well.
so I
So
think
this is really,
So it's really
or times 10, so it's less than 1 milligram per liter.
This makes more sense. I'm sorry, I didn't see that.
Yeah.
That explains, because yeah, I agree that you're not usually going to see high O2 in those other gases. So, oxygen actually is quite low.
Yes, yes. It's less than a milligram per liter.
Okay, that makes more sense to me. Last question I have is more getting back to the Shelby Tube, because I see that as being a really useful instrument.
Mhm.
I see a lot of potential future applications. And I was talking with Kip a little bit about this before, so my question is based on some of his ideas, but when you're doing Shelby Tube measurements, you're getting a discrete measurement in time.
Mm.
And I think someone else had a question about the transient nature of these, or one of the students asked about the difference from March to July, and
Yeah.
of course, it seems like there's going to be seasonal difference in the flow based on the head and stream and other factors. Is there some way that you might envision coupling the point measurements that you get from Shelby Tube with some sort of easier to collect long-term continual data, such as thermal gradient, vertical thermal profiling, where you can install these tidbits or whatever, thermistors, bury them in the stream bed and leave them in data log over seasons, or perhaps multiple seasons? Do you
Yeah.
envision combining the two, kind of like how you would have a USGS stream gauge, which collects continual stage, but then you do point measurements of actual flow with the flow track?
Yeah, I do hope that, that we can develop the Shelby Tube to be more of an automated kind of flow meter. So if we have water and sediment here with the Shelby Tube, and I think that suggestion of the thermistors is a good one, but I'm a little bit curious because so if we had some thermistors here at depth, what my concern was is these thermistors were on the inside of the Shelby Tube, we're disturbing that head, so it's actually not going to be a great correlation. But if those thermistors are outside of the Shelby Tube, that wouldn't be an issue. So I kind of answered my own problem. But the other thing that I think has a lot of potential with the modified Shelby Tube, which is much lower here, there's the potential to have a dilution flow meter, which Kip's other student Stuart is working on, or potentially having some kind of automated system that periodically disturbs the head level and watches that recovery.
And leaving the Shelby Tube in place for a longer period of time?
Yeah, yeah. I think that would be a really great application for them. They're steel, they're pretty robust little measurement devices. If there's some way to automate that, I think it would be
For
really
low gradient
good.
streams, I can see it in a high gradient stream where the stream bed materials are constantly at work, it could be troublesome.
That's a good point, yeah,
Yeah,
yeah.
that's the only question I have. Thanks.
So, John, review for us a little bit the advantages and disadvantages to these compared to the numerous other measurements of measuring discharge that weren't included in this study. We did these point Darcy, but there's thermal method. What other sorts of discharge measurement methods are there? In your sort of literature survey.
The thermal imaging and the heat modeling.
So using heat as a tracer.
As a tracer, yeah, heat as a tracer, doing a base flow separation, more tracers, a conservative tracer. there's those indirect methods, and the Darcian and the seepage meter are the only two physical methods that I know of.
Well, physical or chemical methods, have you heard about people using radon?
Oh, of course, yeah. Using radon as a tracer because of its short half-life. So if you measure stream radon, you can kind of determine the amount of discharge into the stream.
Or what about specific conductance? We had a distinguished lecture just
From Matt, yeah, that's what I was trying to get at with the base flow separation.
Okay. But that fundamentally relies on a mass balance of salt, right?
Correct. Yeah, so there's heat tracer, chemical tracers, radioactive tracers, and the few physical methods.
So, you know, if we were to go back up to Red Butte, and once again try to measure groundwater seepage up there, knowing all you know now, what would you, if we came to you and said, what should we use, what would you say?
In Red Butte?
Yeah.
Knowing what I know about Red Butte, that's tough because the hyperic flow is considerable and there's a lot of variation on the scale of a few hours. So you really need something that can get that short-term temporal variation, but also needs to be able to measure on a pretty large scale. So I would say if you have manpower and could get all these pounded in, the Shelby Tube would be a really useful measurement device, but you would have to have a large number of them deployed in the stream and take multiple measurements throughout the day to try to understand that. To try and get a more integrated discharge, it seems that extended tracer injection and reach mass balance would be really kind of the best way. You know, as you know, the issue with that is that you have to inject it for multiple months to ensure that you're completing all these various hyperic flow paths.
Any other questions from the committee or the
Peanut gallery?
Well, that's your
Water
turn.
temperature. Water temperature, what's the variable water temperature? That's, you know, that stuff about bromide being absorbed has a lot to do with water temperature. How's that factor in?
So the solubility of bromide with respect to temperature,
Yeah.
you know, to tell you the truth, I don't know what that effect is. In general, it'd be more soluble in warmer water than it is in cold water.
And I guess you looked at that or had some kind of a concept.
Yeah, that's really, we're really, our injection is well below solubility.
Oh, neat.
So that's really not an issue of how much bromide we can actually get into the water.
Right.
You know, the water that we're pumping into the stream is a few 100,000 milligrams per liter,
Yeah.
and we're measuring 4 milligrams per liter.
Okay.
And that few 100,000 is still below bromide solubility,
Neat.
so it's not really an issue.
We just needed a bigger pump.
Yeah,
I'm sorry?
And we just needed a bigger pump,
Uh-huh.
and
a
more.
bigger tank and more bromide.
Get it in there.
Yeah, yeah,
And a
a
babysitter,
babysitter,
yeah.
our pump kept
They
stopping.
use that stuff in the hot tubs, you know.
Bromide?
Yeah.
To sanitize them?
Yes,
Chlorine.
yeah, it's like instead of chlorine.
Uh-huh.
The temperature brought up a good question.
Sure.
I have for you. The difference in water temperature between the West Bear Creek summer and July and March, what was the difference in degrees C and temperature of the stream on average? Just rough, doesn't have to be.
That's a good question.
It's not that important.
Yeah, I'm trying to.
But there was a pretty good difference, right?
It was a few degrees.
That's all, okay.
Yeah. Though you're referring to the stream water.
Stream temperature.
Yeah. I don't have that off the top of my head. I know that that data is available, that we did collect that, but I don't know what it is.
Follow-up question, just assuming it was, say, 10 degrees,
Mhm.
what would you expect the impact to be on hydraulic conductivity? Is it viscosity or density of water that would give us a more temperature-dependent effect on hydraulic conductivity?
For ambient temperatures, I believe that I explored this when our initial Shelby Tube did not match well with the falling head permeability test that we conducted in May. And I was wondering if there might be the difference in temperature between the surface water and the groundwater, and that you're pouring surface water in there, if that would have an effect. My calculations showed that that wasn't an effect. Whether that was the viscosity or the density that was a bigger change, I can't remember, but I'm trying to, the density doesn't really change until it starts going to its phase change.
That's right.
So I would imagine it was the viscosity.
And do you have any idea, saying what relative change in temperature would half the viscosity, say going from 25 degrees C, how far down do you have to cool the water to get half the viscosity or half the hydraulic conductivity? Any idea?
I don't know what the effect on the viscosity would be. On the hydraulic conductivity, it was significant. It was to change the hydraulic conductivity, I think it was close to 20 degrees.
That's right, yeah. 20 degrees with about half the viscosity and half the flow. And that's, I know you always compared apples and apples because you're comparing these with the same spring or summer conditions, but there's a lot of the variability you might see in seasonal flow could be temperature dependent because of the thicker water base.
Oh, okay. So you're suggesting that the differences in stream bottom conductivity could be described by water temperature?
Yeah, because it's not just intrinsic permeability, it's not just the aquifer solids that you're measuring. But
Do you know, can you write the relationship between hydraulic conductivity and permeability?
Yes, I might be able to see here. So hydraulic
conductivity.
Yeah,
okay.
hydraulic conductivity is related to, I believe it's rho G permeability mu, viscosity.
You're close.
I'm close. I haven't twisted up.
He's got the four components.
got it.
Give him a break.
Yeah. So what is it? It's rho.
One question.
Would hydraulic conductivity be inversely proportional to permeability?
Yeah, that was my question.
No, yeah, it would be directly proportional.
So
So-
let's move.
It'd be rho K over mu G. Well, G needs to stay on top.
Leave G there.
Yeah.
Yeah, now you've got it.
There we go.
Yeah.
So,
So K presumably stays, little k stays the same,
yeah,
G stays the same. Rho and mu could change, but if mu changes by a factor of 2, so does, the sediments haven't changed, the permeability hasn't changed, but
Right.
hydraulic conductivity,
can.
yeah.
Yeah, and yeah, I did explore that, you know, when I was trying to explain the difference between the Shelby and the falling head, and there just wasn't enough temperature gradient between the stream and the groundwater. Yeah.
That's interesting, because you have a thermal coefficient from the earth. with the
Yeah,
water
you have the
number.
geothermal temperature gradient
Yeah.
that is affecting the groundwater, and it stays pretty much at the mean atmospheric temperature
Sure.
for the area.
Okay, we'll excuse everyone except the committee.
Oh, sure.
And including John.
Okay.
And don't go too far away.
Yeah.
We will deliberate and then
Go ahead and close this down.